Hello, this is Peter Newman. I'm showing today latch mechanism analysis part 3, tolerance analysis, and you should definitely look at part 1 and part 2, especially part 1 to see what these parts do and their functions and their requirements and the design changes that were made to improve those requirements. And that was all done on the nominal CAD geometry. And in this video, I'm just giving a little taste of something some of you may not have seen a lot of, which is tolerance analysis. And it's the effect of the variation on the dimensions of the parts and how that can affect the function. So we have a drawing for each part, and say a poor quality drawing such as this will show minimal dimensions with a general tolerance where anything on the part, so long as it's within plus or minus 0.2 millimeters of its CAD nominal, is an acceptable feature. So this drawing doesn't really call attention to what's critical about the part, and this change to call out the critical dimensions will be seen why that would be a smarter way to dimension this part. There's a pivot point here, and this is what I call the backstop. And back in the function, the spring is pushing this key down again, and the backstop makes contact here to set the locked position of this red part. And the other critical dimension is the distance from the pivot to the backstop on the mating part. And again, the more direct call out would have been here. So we're going to simulate a worst case condition is if this red part gets longer and the blue part gets shorter at the backstop position, the assembly can't reach this position, and we're going to just model that directly in SpaceClaim by moving faces around. So here we are in that assembly, and if we open the lock part, we can choose some faces to move around, like these faces up here. And those faces, if we hit the M for move key and say we want to move up 0.2, jumps up a little bit. And then if we go and edit the base, the cone component, which is what the key is mated to, we can do a move on the face along the axial direction in this direction to shorten it up by 0.2. And so with those two changes, when we go back, we notice there's an interference. And so to roughly estimate where the locked angle would be, we can select the component, the lock component, and we can do a move and rotate that about the center, and we can just move it by hand until we estimate, and I've already done it more precisely by eye. 2.4 seems to be the point at which these parts just come into tangency. So this all of a sudden doesn't look like a very secure locking angle, and the next part of the video is a small design change that will significantly improve how this looks. And to get there, we're going to do File, Save As, and put all of these into a better condition and save those. Every external document is a new version. This is a way to keep the original separate from the new parts. So I've done that. So now we can go and change the design. So the changed design is to open that lock feature and realize that a lot of the problem was that back in the assembly, if we look at the plane and cut through that, the contact point is down here, and it moves up here closer to the pivot point, making making a small motion here turn into a large motion at the other end. And so a better design is to actually take that lock and delete these two faces off there so that the contact point moves forward further away from the pivot. And then the other problem we noticed is when this part rotates, the contact point moved from where it was at the end down the part as this face was parallel with the other. So another improvement in the design is to take these couple of parts and rotate them around the front. And to do that, I'll actually split the part in half. So I'll select the two sides, put a plane in, split the body with the axis, and that'll make it easier to rotate some faces about the front. And let's try rotating maybe those faces, and we will move and drop this on that front vertex and just put a couple of degrees of rotation on that, 3 degrees of rotation. So now I can mirror the part back to get the full part back. And then in the assembly, what we can see is the contact point has now moved further away from the center hole, and so the same 0.2 millimeters of displacement is a larger lever arm from the pivot, and therefore there'll be less motion at the other end. So this is the improved design, and we can do File, Save As, Connector Assembly 3, every version as a new version. So we can close this up as the nominal, as the improved CAD nominal, and instead open up Connector Assembly 3 to apply the variation. So we'll go ahead and open the lock, and this is the new design, but we're going to move that same tolerance on these features. I think I pulled that and that along there. We're going to move in this direction by that control key. We want to move in this direction by 0.2. And we'll go to the cone, open that, and move by the same 0.2. Move along this direction, that by 0.2. And so back at the assembly, we do see the same interference showing up. And we need to resolve that, but when we rotate the component under assembly, or select components and we want to select the lock and do a move on that. Now we only need to rotate about 1 degree. I'll just there, 1 degree. So 1 degree resolves the interference, but the point here is that this improved design has caused less motion and the locking function is more secure in this design than the original design. And that is the point of this video, is to be aware of how tolerances can affect the functions that the assembly has to produce. Thanks for watching. Bye.